everyone. Welcome to the semester 2, week 8 lesson. This is our last lesson for the summer in semester 2 review for pre-AP pre-cal. So I'm going to hit the highlights of what we covered in the earlier weeks. I'm not going to review over matrices because we just learned about that last week with the systems review. I'm not also going to review the sequences lesson because that's also fairly new, but I do want to definitely review the things that we covered in the first 5 weeks. That's what I've chosen to, that's what I've selected to kind of do my cumulative review over. So the very first week, and you can always have your guided notes handy for any of these if you need to refer. I'm not retyping out a bunch of rules and things when they're already on a previous set of notes. So I'm just verbally going over the types of problems that you'll see on the assignment and remind you how to do those. So in the first week, we worked a lot with functions, particularly with inverse functions and also with composite functions or function composition. I also reviewed with you what a function looks like, what the definition of a function is, as well as what a one-to-one function is. And a one-to-one function means that a relationship is a function, and the inverse of that relationship is also a function. That's a one-to-one function, is when both the original and the inverse are functions. All right, so first we're going to do a composition, and when we read this, it says g of f of -1. The letter closest, or the function name closest to the number that we're putting in, is what you need to deal with first. So the first thing I need to do is figure out what is the function, the f function's value when I put a 1 in for x. So I'm going to put a -1 in for x. And I get, this is 1 times 2 is 2. This is a +1 and a +1. So that's going to end up giving me 2 plus 1 plus 1, which is 4. Now I'm going to take that 4 and I'm going to plug it into the g equation. And that is going to give me 5 times 4, which is 20, plus 15, which is 35. And so this would be my answer. So make sure you pay attention. If it had said f of g of -1, I would have started with g and then taken that answer and plugged it in for f. This said the reverse. Determine if the following is a function and if it is a one-to-one function. So what we're looking at is this relationship, these 5 points, is this a function? We're looking for repeat x's. I have 7, 8, 1, 0, 4. Those are all unique. So it is a function. So I don't want to choose this. Now, if it's a one-to-one function, that means the reverse, that point, this point reversed, this point reversed, and this point reversed. Is this also a function? Now, you don't even have to reverse these. You could just look at the y values. If it has no repeat x's, it's a function. If it has no repeat y values, that means the relationship is a one-to-one function. And that is true here. So we're going to say it is a one-to-one function because we had no repeat x's and no repeat y's. If we had no repeat x's, but we did have repeat y's, we would have chosen this one, that the original was a function, but the relationship is not a one-to-one function. Which function is not a one-to-one function? So basically, you could just kind of eyeball these. I mean, if you look at this, this is a 4th power polynomial with a negative in front of it. So it's probably going to look something like this. It is a function, but if I found the inverse of it, it's going to look like this. That is not a function. So I already know it's this one, but I'm just going to prove it to you. This is an exponential. That's a function. The inverse of an exponential is a logarithm, which is also a function. This is a line, negative sloped. The inverse of that function would probably look like this. That line is also a function. And then this is a square root function. It probably looks something like this. The inverse of that would look something like this. That is also a function. So this is the only one where it's a function originally, but the inverse of it is not a function. Any even-powered polynomial is not going to be a one-to-one function, just like a quadratic is not a one-to-one function. All right, graph the inverse of this provided graph. Remember, The inverse of a graph, you just need to locate some points on this line. This says at least 5. On your Delta Math assignment, you will see the grid lines, so you'll be able to tell very clearly what are points and what are not. And then we are going to flip those points, the x's and the y's, flip them so that we can graph the inverse. So I'm going to tell you, because I already did this, that negative 4, 2 is a point. So that means our inverse, we need to plot to negative 4. 0, 2 is a point. I'm sorry, that's not true. 2, 0 is a point. So we're going to be plotting 0, 2 on our inverse. Negative 1, 1 is a point, which means our inverse, we need to be plotting 1, negative 1. 8, negative 2, negative 2, 8. And then I think we also have a point at, let's see, yeah, 5, negative 1. So that would become negative 1, 5. So if I were to go plot those points, negative 1, 5, 2, negative 4, 0, 2, 1, negative 1, and negative 2, 8, what you'll see is that forms a perfectly straight line, and that is the inverse of the given line. Remember, if we're looking at two graphs, we can tell their inverses of each other if they reflect over this line of reflection, which is the linear parent function. It's always a way to tell graphically if something is an inverse or not. So you can very quickly see, oh, yep, if I turn my head sideways, those are reflections of each other across that diagonal line. Okay, what about if you're given an equation of a function and you're asked to find the inverse? And remember, that little negative 1 power tells you that you're looking for the inverse. And you may not be able to see this, but that is a 5th root. So remember, to find the inverse of an equation, you're going to take this y and this x and you're going to switch them. And then we're going to solve for y. So our idea is that we need to isolate this radical. So I'm going to add 2. And then I'm going to divide by 9. So I end up with x plus 2 over 9 equals the 5th root of y plus 4. If I want to get rid of a 5th root, all I have to do is raise whatever, both sides to the 5th power. So now I have x plus 2 over 9, that whole fraction raised to the 5th power. And now I just have y plus 4. The radical and the power cancel each other out on that side. And now I'm taking a minus 4 and putting it behind that 5th power parentheses. And so this is what I end up with, and that is what my inverse is. Once you get y solved for, you can rewrite it in function notation. So if you look at this, the only one it could be is this one. Oh, that's the only one that has things happening in the correct order to be the inverse. We can also do that with a line. This is a much simpler example. I'm going to switch x and y, and I'm going to solve for y. And after the last problem we did, a linear one should seem like a gift, right? And so when I solve for y, I end up with that the function's inverse is x plus 11 all divided by 3. And this is a plus. You would be able to tell that on your actual assignment. Sorry, my grid lines are really not putting out. It's the last week and my printer's tired. Okay, so we're ready to move on to week 2. Week 2's lessons went all about, we did talk about some polynomials, but really we were specifically, the lesson was to cover the difference between real solutions or roots or zeros and imaginary. And so that brings up the letter I, and that brings up a review of complex numbers. So we started out with just graphs and you recognizing that you could build a very simple equation just by identifying the roots. Now this is a cubic function, you can tell, and it does actually have 3 visible roots or zeros, -5, -1, and +1. So what I want to do is write those as factors. -5 solution would look like an x plus 5 as a factor. X minus 1, a -1 power would look like this, and a +1, not power, -1 solution would look like this as a factor, and a 1 as a solution would look like this. And you don't see this 3 separate parentheses. These two could be multiplied together to be a difference of squares. So that's where this comes from. But I want a +5. So this doesn't have the right sign with the 5, neither does this. And these two multiplied together could not possibly give you this. That would be if these were 2s, but because they're 1s, we want to go with this one. And then could you do that on a y-intercept one? Now this one says, write a function in any form that matches this graph below. Matches means it has to be perfect. This was sort of an approximate. This could be, it said it could represent this graph. This one, you want it to perfectly represent this graph. So I can see it's a quadratic, and I can see that I have solutions that look like -6 and +1. Yeah, -6 and +1. But I've also been given the information that I have a y-intercept here. That's going to allow me to get the perfect a value. So a -6 as a factor, a -6 solution would be written like this as a factor. A -1 solution would be written like this as a factor. All I need now is to get the a value for this graph. I know it's positive since this is a positive parabola, but I can use this y-intercept of 15 to solve, and the x-coordinate of 0 that accompanies a y-intercept to solve for a. And so what I end up with is this is 6, this is 1, 6 times 1 is 6. And I can easily solve for a by reducing this fraction to 5/2. So my equation is exactly 5/2 x plus 6, x plus 1. You could multiply these two together. You could put this in standard form if you want to, but this is the easiest, quickest way to get a final answer. And they'll accept it. It says in any form, so we can keep it in intercept form like this. Okay, for the following equation, determine the nature of the roots. So now we're getting to a place where we're recognizing that unlike these where we had all visible solutions, we could possibly have solutions that are not visible, that are imaginary. And so the way that we determine the nature of roots with a quadratic is with the looking at the discriminant part of the quadratic formula. And remember, the discriminant is that b squared minus 4ac value that's inside the quadratic formula's radical. And so if you look at an equation that's been given to you in standard form, it is set equal to 0, then you clearly can see your a, your b, and your c values. And you can find out, are these real solutions or are they imaginary? So I'm going to do b squared minus 4 times a times c. And what you're going to end up getting, and I forgot to do this calculation, I just have the answer. Let me get to my calculator. 24 times 24 minus 4 times 2 times 72. You end up getting 0 for your discriminant. So that's interesting because that is not negative. So it's definitely not imaginary. But we're going to have two solutions. So when we do negative b plus or minus the square root of this discriminant over 2a, the square root of 0 is basically saying I'm not going to be adding or subtracting anything to this numerator after the negative b. So I'm just doing negative b over 2a. That means I'm only going to have one solution, and it's going to be repeated. Since it's a quadratic, if I only have one solution, it really means it is one of these that has a bounce, like this. Okay, it has one solution, so it is real, and it's going to be this equal because it's going to have the same solution, and we're going to have two factors that are identical, representing that one solution. It has multiplicity, if you remember. So this has a one solution with multiplicity. So multiplicity of 2. So they will be equal solutions, the same solution twice, basically. Okay, now we're going to practice some complex number practice. So I want you to recall that I is the square root of -1. I squared is just -1. I to the third power is -1. I, and I to the fourth power is positive 1. And that is always true. I mean, this is just saying the square root of 1, a square root of negative 1, but if I multiplied it times itself to get I squared, the radical would come off the negative. It would just be negative 1. If I multiplied this by another I to get I to the third, well, now it's just going to be a negative I. And then if I take negative I and I multiply it by another I, it'll end up being negative I squared, which we know I squared is negative 1. So negative 1 is positive 1. So we can use this pattern and continue as high a power as we want. It's just going to keep looping. I to the the fifth will go back to here. I to the sixth will come to here. I to the seventh, I to the eighth. And it will keep going like that. Now, I to the seventh is going to be this one right here. Remember, what you do is you divide the power by 4, and that tells you where in this this pattern it falls. The remainder does. So if I divide 7 by 4, it's going to do a complete set of 4, and then it needs to go 3 into another round of that pattern. So this is going to be 8 times negative I. This is I to the 37th. So 37 divides by 4 9 times. And then it has one remainder. So it's going to go to right here. That's just going to be I. This is 68. So 68 divides by 4 perfectly. So it's going to end up right here. So this is going to be negative 11 times 1. And then 41st power has a remainder of, I should do that, I guess. Has a remainder of 1, so we're going to go back to just I. So let's look at this answer. If I were to simplify, this would be negative 8I plus 4I minus 11 plus 11I. I have a lot of i's. I definitely have just a negative 11. That's the real part of this answer. And this reminds you, put the real part first and the imaginary part second in your answer. I end up with 11I and 4I, that's 15I, minus 8I, that's 7I. And that would be my answer. Is that right? Yeah, that's right. Okay. So hopefully you remember how to simplify powers of I. Can we add complex numbers? Yes, you add the real pieces together, you add the imaginary pieces together. You can also do that with subtraction. Just make sure that if this was a minus sign, you distribute it to the signs of everything that comes immediately following the minus sign. So this is going to be a positive 1 plus a 12, that's 13. This is going to be a negative 6I plus a 1I. So it's going to give me a minus 5I. And that's my answer. Simple as that. Now we can also multiply. And just remember that when we multiply, anything that has an I in it, or anything higher than a power of I to the first, so if it's I to the second, I to the third, we'll have to simplify. But we're still going to use FOIL or box method. And then this will be 10I squared, and we need to simplify that. So 10I squared is really 10 times negative 1, so that's really a negative 10 right there. So I have negative 12 and negative 10, that's going to make negative 22. And I have a 10I minus a 12I, that's going to leave me with minus 2I. And that is my answer. And then this one says, what are the roots of this in simplest form? So they're kind of telling you this is going to be a complex solution. This is a quadratic, so I have to use quadratic formula to find imaginary solutions when it's in standard form like this. So A is 16, B is negative 32, and C is 17. So I'm going to go ahead and do the discriminant work first. That would be negative 32 squared minus 4 times 16 times 17. That's going to be big. And it's going to be really small. It's going to be negative. So I'm going to solve that. 32 is 1024. And then 4 times 16 times 17. So it's just barely negative, actually. 1024 minus 1088 is negative 64. Okay, so I have negative b, which is also negative, plus or minus the square root of negative 64. I'll have to simplify that, over 2 times 16. So this is our negative b plus or minus the square root of b squared minus 4ac, which is what we did over here, all over 2a. So we'll end up with 32 plus or minus. We can take the square root of negative 64. We're going to take the I out. That'll get rid of the negative, and the square root of 64 is 8. So this is 8i over 32. Now, if every piece of the numerator and denominator can be reduced by a common factor, you can do that. And I see that I can take an 8 out of all of this. Am I right? Yeah. So, and actually you could even simplify it as 32, take the real piece over 32 and the imaginary piece over 32 and simplify that way. That's actually easier. And that would end up giving you 1 plus 1/4 I. You could also write that as 1 plus I. No. You could take an 8 out of all of these and it would be 4 plus or minus I over 4. That would be how you'd have to write it. 4 plus or minus I over 4. That would also work. Either one. Okay, we're done with that page. Oh, we still have one more. What about if we are given two complex roots and they want us to write it as a quadratic equation? Well, I think I taught you guys. There's a hard way to do this and there's an easy way to do this. Now, when I was teaching Algebra 2, I did not teach the shortcut. I wanted you algebraically to be able to take these roots and put them in, put the positive root into a factor, and also the negative root into a factor. And simplify, and then multiply together. Now, I believe that I taught you in this unit, in week 2's, or lesson 2's unit, that you can actually really do a shortcut. You can always assume that A equals 1 in these types of problems. And what you're going to do is find the negative sum and the product of these roots. This is going to give you the B value, and this is going to give you the C value. So if I add these two together and take the opposite sign of that sum, I'm going to get my B value. And if I multiply these two roots together, I'm going to get my C value. And it's actually quite easier than this long algebraic thing, but you would see that we would get the same answer no matter what. So if I take negative 6 plus 3i and I add to it negative 6 minus 3i, my 3i's cancel out and I just end up with negative 6 and negative 6, which is negative 12. But I want to change the sign because I have to have the opposite sign of the sum. So B is 12. Now I can also take these roots and multiply them. And remember, you're taking the positive and the negative, and we are multiplying. So we get 36. Here we get plus 18i. Here we get minus 18i. And here we get minus 9i squared. These cancel out. Remember, I squared is equal to negative 1. So this becomes 36 plus 9, which is 45. There's my C value. So I have an A, I have a B, and I have a C. And I'm ready to write my quadratic using those numbers. And this would be the quadratic equation that if we solved, we would get these roots. You can always test that too if you have time. All right. So now we're ready to move into week 3. That was all exponential work. Some things were very simple, like can you convert a radical into a fraction exponent? Remember, the index is the outside number. If you don't see anything there, it's a 2. The power is the inside number. This is the numerator of your fraction exponent. This is the denominator. If you don't see a power in here, then it's a 1 as far as the fraction exponent's numerator. But I do have numbers in both places. One's a 2 and one's a 7, and that's the order it should be written in. And that is your answer. Now we also have to remember some things about exponent rules. This is a, we're looking for what's equivalent to this right here. So basically, if you see a fraction exponent, what can you do to switch it into radical form? So it's on the bottom. So we definitely still need a fraction answer. The only time we wouldn't is if this was a negative exponent, because that would tell us that we need to move that to the numerator. So what we have left, this would be 1 over 2x plus 3 inside a square root because of that sorry, my dog is just whining incessantly. That is telling me that it's a square root, and that is telling me what the power should be. And so we want to pick the answer that has the 5 in the right place and the 2 in the right place. And the 2 is never visible, but it is there. And that means it's a square root, and that would be this choice. Can we simplify an expression that has a fraction exponent that needs to be distributed using the power property to all of these things, to the 16, to the x to the 4th, and to the y to the 7th, y to the 12th. And this is a 5 halves power. Oh my goodness, my dog. Okay, so I'm going to take 16 and I'm going to raise it to the 5 halves power. I'm going to take 4 and multiply it to the 5 halves power. And I'm going to take the power of 12 and multiply it times the 5 halves power. And what I will end up with, oh, this is a negative 5 halves, isn't it? Yeah. And this is a negative 12. Okay, sorry, negative 5 halves power, and that's one of those things that you can see on your Delta Math, but it didn't print out very well for me here. So anything that ends up simplifying to have a negative power is going to have to go down below. That's just the rule. So the 16 is definitely going to have to go down below. The x is going to have to go down below. The y is going to be allowed to stay because these two negative powers are going to cancel each other out when we multiply. So I'm going to end up with y to the 12 times 5 halves is 60 over 2, which is 30. So that is definitely my numerator. This is coming down below. 16, that now is a positive 5 halves. And x being moved down here, this is 4 times negative 5 halves. That's negative 20 over 2, which is negative 10. When I move it down to the bottom, it's positive. And the only thing that's left is I can't have a fraction exponent down here. Can I simplify this? Or can I put it into a calculator and see what 16 to the 5 halves power is? I mean, 16 is 4 squared. So 4 squared raised to the 5 halves power is really just 4 to the 5th, which is actually just a whole number, which is 1024. We've seen that number before. So this ends up being my answer. Okay. Can we graph an exponential? Let's remember reference points and what types of asymptotes an exponential have. An exponential has a horizontal asymptote, and it's the value. The equation is the value of this at the back. If you don't see anything added or subtracted after the exponential, then it's at 0, like the parent function would be. So I'm going to choose horizontal. It's going to bring a horizontal asymptote up here, and we're going to drag it to the 3. So I'm definitely going to end up seeing this right here. All right, then I need reference points. Now my reference points, this is decay. Okay, decay has these reference points. 0, 1, and negative 1, comma, the reciprocal of the base. If it was growth, it will be 0, 1, and 1, comma, the base. And then you will change them by the x coordinate will need to be changed by any shifts left or right, the opposite of what it looks like. And the y coordinates of these reference points will be changed by, if there's any a value in front of the base, it would need to be multiplied by that. And then any k value either added or subtracted. So we definitely have a decay situation here. This is a base that is smaller than 1. So my reference points originally would be 0, 1, and negative 1, the reciprocal of 1/5. And then what I need to do is adjust those points. That would be for the parent function, if it was just 1/5 to the x power and nothing else. But this has more going on than just 1/5 to the x power. So I see a +4 up here in the exponent. That means my h value is actually moving to the left 4. So that means all of my x's need to be moved to the left 4. I don't have any a value to contend with, so I don't have to multiply these y's by anything, but I do need to add k to them. So I'm going to take those y values and add 3. So all of these x's, I'm taking away 4. That's going to give me those. And all of these y's, I'm adding 3, which is going to give me these 2 points. I'm going to drag these 2 points to those 2 places. So negative 4, 4, and negative 5, 8. And you should see a picture of an exponential decay graph. Okay, that's what you should see. That should match. All right, now, can I look at a picture of an exponential, in this case it's growth, I can tell. I can tell because that base is greater than 2. But can I identify important things about this? Now, I definitely can see where it's horizontally flattening out. This is an exponential function. I can tell that. The horizontal asymptote, exponentials will always have a horizontal asymptote. And the equation for that asymptote appears to be -5. So you'll choose y equals here, and you'll type in the number -5. Now, the range for an exponential is always restricted by this exponential. So make sure that you notice that -5 is a restriction on the domain, and everything is above that. So I want the range to go from -5 to infinity. It cannot include -5, and it cannot include infinity. It does go to the left and the right forever. So if you look at this, it is increasing. If it was decay, we'd have decreasing written there. And the domain is all real numbers, which looks like this in interval notation. In the behavior, on the left side, if we look at this, as x approaches, and x goes on forever, we're using this part of the domain here. As x approaches -infinity, what's happening to the y values? They are approaching what boundary? They're approaching, the y values are approaching -5. Now, if I look at the right side of this graph, the other part of the domain is going up towards infinity. It's going to the right towards infinity. Well, what's happening to these y values? Well, they're going up forever too. As it goes to the right, it goes up forever. So if you notice, these two end behaviors use the domain, and these two use the range. Okay. The order, though, does matter. So you have to pay attention to the graph to know which range values go in which places and which domain values go in which places. And then we've got one more exponential that I wanted to cover. Remember, you can solve an exponential without any logarithms if you can identify that these numbers could be rewritten with a common base. Now, these are multiples of 2, I believe, but they're also multiples of something even bigger, which would make the equation a little easier to solve. This is a multiple of 8. This is 8 to the third. So I'm going to rewrite this down here, 8 to the third to this power. I think that's a plus, actually. Am I right? Yeah. And this is also a power of 8. 4096 is 8 to the fourth power. And so here's the good news. When you can get an exponential equation set equal to each other and you have a common base, you can ignore those bases and just set the exponents equal to each other. So I'm going to distribute this. This would be 15x plus 6. I'm going to just lose the 8 because I know I've got the 8s on both sides. And then on this side, I have 20x plus 44. And I'm just going to solve for x. And that's going to give me my solution. And I think this gives me -38 equals 5x. And so x will be equal to -38 over 5. And that is it. That's my answer. You don't have to check exponential solutions. You do have to check logarithm solutions, okay? Because logarithm solutions, think about it. You don't have to check exponential solutions really, other than just checking that your math is right, because the domain is all real numbers for exponentials. There are no undefined values for x. That's not true in a logarithm, because a logarithm doesn't have a horizontal asymptote. It has a vertical asymptote, which is an x value. That is where the function is undefined. So let's remember that logarithms are the inverse of exponentials. So everything about logarithms is completely the reverse of exponentials. We can convert between the two forms, which is really helpful when we're trying to solve or evaluate. The graphs are inverses. They have opposite types of asymptotes. Remember, exponential has horizontal, logarithm has vertical. The reference points are flipped. So instead of 0, 1, we have 1, 0. Instead of 1, the base, we have the base, 1. Or if it has a decay type of base, it's going to be 0, 1 becomes 1, 0. -1, the reciprocal of the base becomes the reciprocal of the base, -1. Once we understand that inverse relationship, we can solve. But we also first need to just remember our properties of logarithms. And they're a little bit similar in some ways to our properties or rules for exponentials, exponent rules. So you may be asked to condense a logarithm. That means you're going to see more than one logarithm in the expression. Can you use properties to condense it into one logarithm? So if I see a minus, that means, and remember, these logarithms have to have the same base. And because I don't see a base written down below as a subscript, I know they're the same base, and they're a base of 10. If you see a number right in front of a logarithm, it can go back into the power of the argument. And the argument is the thing that immediately follows the word log. So this is really log a to the third minus log q to the z power. If you have logarithms being subtracted, they can be condensed into a single argument with what was before the minus sign written in the numerator and the argument of the logarithm after the minus sign being written in the denominator. And this would be my answer. This is what I would write right here. You don't have to write the word log. It's already there. You're just writing what would go inside the argument. Can we do the reverse? Can we expand? Can we take an argument that looks like it has multiplication happening up here and it has division happening down here? So that means I'm going to have some addition of logarithms and then a subtraction. So I'm just going to start by rewriting this numerator. This would be log x plus log the cube root of z squared. Can be written like this. Okay, and then I would do minus to get this down here, log y to the fifth. Now the only thing that prevents this from being fully done is that I can also bring those powers in front of the individual logarithms. So 2/3 can come in front of log z like this, and 5 can come in front of log y like this, and that would be my answer. And that is an expanded form. Now, what if they ask you for the value of a logarithm? So you have to remember that when you're evaluating or finding the value of a logarithm, you're basically kind of putting it into an exponential form. You're like, this base of 4 to the what power is going to get me the fifth root of 4? Well, it helps me to remember that I can rewrite this as a fraction exponent. This is an invisible 1 over the index of 5. And so 4 to the what power gets me 4 to the 1/5 power? Well, it would just be 1/5. That's what I want. 4 to the 1/5 power equals 4 to the 1/5 power. That must be the right answer. Okay, let's look at graphs of logarithms. Completely the inverse of exponentials. So remember, we're going to have a vertical asymptote. And when you choose that, it's going to bring up a vertical dashed line. And you are going to drag it to the opposite x value is what you see in parentheses with x. So in the argument, anything added or subtracted to x is your h value when you change the sign. So I'm actually moving this to the left 7, which is going to end up bringing it starts at 0 and you're going to move it over. So x equals -7 is my asymptote. Now my reference points, let's look. This is a base of 3. So normally it would be 1, 0 and 3, 1. Those would be my reference points. They're the inverse of what they would have been for exponentials. Normally, for exponentials, I'd have 0, 1, so I'm writing 1, 0. And for exponentials, I'd have 1, 3, so I'm writing 3, 1. But we do need to apply that h value where we moved everything 7 to the left. If we move the asymptote 7 to the left, everything gets moved 7 to the left. So I'm going to take away 7 from 1 and from 3. And then I do have an a value that needs to be multiplied to all of the y's, -2. There is no k value behind the argument, so I don't have to add or subtract anything to the y values. I just need to multiply them by -2. 0 times -2 is still going to be 0. 1 times -2 is going to be -2. So I'm going to drag one of these points over to -6, 0, and one of these points over to -4, -2. And at that point, you have a picture of a logarithmic function. Okay. Now here's a picture of a logarithmic function. They want you to answer some questions about it. And remember, it's exactly the opposite of what our exponential answers were as far as its features. So this is a logarithmic function. I can tell because it's flattening vertically, not horizontally. This flattening is happening like this. It is a vertical asymptote, and I can tell that it is x equals, and it looks like 2 is pretty much where it's flattening out at. The range is now what's unrestricted. Okay, it goes up and down forever. There's nothing horizontal to block it from going up and down forever. This particular logarithm is decreasing. I mean, if you read it from left to right, it's definitely falling. And the domain is where the restriction is. It is staying to the right of 2, and it doesn't even include 2 because that's an asymptote at 2. So the end behavior, as it goes towards the left, what the x values are approaching 2, but the y values are increasing forever up. Okay, so we're using this part of the domain and this part of the range. The end behavior to the right, if we read this graph going to the right, the x values are getting larger forever, and the y values are going down forever. This is decreasing on this end, so it's going towards negative infinity. So again, we still use both pieces of the range, not necessarily in the order that it was originally written, and we do use both pieces of the domain in our end behavior. Okay, and then can we solve some log equations? That's what the rest of this practice is. Now this doesn't ask us to solve. It just wants us to write it as an exponential. So let's remember that when we have logarithms that are written like this, they can also be rewritten like that. So that's what I'm going to do. I'm going to take the base, 9. I'm going to take the answer that I was told that it was equal to. That becomes my exponent, and the argument becomes my answer. And this is all. They don't want you to solve. They just want you to practice. Even something complicated like this can still be written in exponential form. Okay, now we're going to solve. So there's multiple ways to do this. I kind of think of it like exponential. 2 to the x power equals 16. How many times do I need to multiply 2 together to end up getting 16? It's 4. Make sure you always check your answer. If you put in a logarithm solution back into the equation and it creates a negative base or a negative argument, it is not allowed to be used as a solution. Okay. Let's look at the next problem. Log base 4 of 216 equals 3 halves. So x to the 3 halves power is 216. Well, you can do a couple of things with that. You could get rid of that power by raising both sides to the reciprocal, because when I multiply 3 halves times 2/3, I just get x. And so that tells me whatever 216 to the 2/3 power is. Now I'm going to tell you, 216 is 6 to the 3rd power. I'd like to rewrite it that way because when I multiply these powers together, those 3's cancel out and this becomes 6 squared, which is 36. And yeah, that works. 36 would be our answer there. Could I use properties of logarithms? If I see more than one logarithm and it's in the form of a subtraction or an addition and they have the same base, it would be very easy to convert that into a single logarithm. A minus would tell me that it's a division argument. So this goes on top and this goes on bottom. I can simplify that. That's really just a 2x, isn't it? So log base 3 of 2x equals 4. And now let's convert it into exponential form. 3 to the 4th power is 81. All I have to do is divide by 2 and 81 over 2. Now I need to double check. If I plug that in here, will that keep this particular, where there's an x, if I put 81 halves in, will that stay positive? Absolutely. So I can use that. Can we do that with a slightly more complicated problem? This has a quadratic in it. Yes, I can still use those same properties. So log base 6 of an argument that has this on top and this on bottom equals 1. Yes. And then I can absolutely set that equal to an exponential. This is just 6. I can always stick a 1 underneath it. Cross multiply. This would be 4x squared minus 7 equals 6 times 4x plus 1. Distribute. That's 24x plus 6. And I would move both of those to this side. So I end up with nothing on this side. And I have 4x squared minus 24x minus 13 equals 0. I need to factor this, okay? 4 times negative 13 is negative 52. Factors of negative 52 that add up to negative 24 would be negative 26 and 2. But I have to divide by the a value, which was 4. So this reduces to 13 over 2. I'm going to put the 2 in front. And this reduces to 1/2, and I'm going to put the bottom number of 2 in front. Oh, yeah, I could have just set these equal. So this is 13 halves, and this is negative 1/2. Can I use both of those? Well, I need to make sure. If I put these into either of these places, will I have a positive argument? I would here, because anytime I square 13 halves or negative 1/2 into here, it's going to be positive. Times 4. Actually, negative 1/2 doesn't even work here, because negative 1/2 squared would be 1/4. 1/4 times 4 is 1, and 1 minus 7 is negative. So this does not work. The only one I can use is 13 halves. Can we use natural logarithms the same way we use common logarithms? Absolutely. If I want to solve, I need to isolate the logarithm. So I'm going to add 12, which gives me 12 on that side, and I'm going to divide by 2, which gives me 6. Please don't forget that a natural logarithm has a base of e. So when I write this in exponential form, that e needs to show up as the base. It's not visible, but we know it's there. I'm going to take away 6 from that exponential. Take away 7 from that exponential. And then I'm going to divide by 8. This wants the exact value, so you should not be typing this into a calculator. You should be writing e to the 6th minus 7, all divided by 8. That is the exact value of x. And then the last exponential problem, and actually it's exponential to start, but it ends up being a logarithm to finish off, is one of our investment problems. If we invest $9,000 in a bank, that would be the principal. That's your P. The bank pays 6.25% interest. So as an interest rate, that would look like this. Compounded quarterly means the end value is 4. And they want to know, when is it going to reach 13,600? So basically, I'm setting this problem up by putting all the right pieces in the problem. Don't forget that the end value shows up in 2 different places. T is what I'm solving for. How long will this take to mature to 13,600? So the first thing I want to do is divide by 9,000. And I put all of this into a calculator exactly this way. That's going to cancel out the 9,000. I go ahead and do all of this in my calculator. So if I divide 0.0625 by 4, I get, I've done this already because I knew I would need to. Where are you? Oh yeah, I get 0.015625, and I'm going to add 1 to that. So basically I'm getting this, and that is being raised to the 4t power. So the problem is that I need to convert this to a logarithm to be able to solve. So I'm going to put a log on both sides, or I can actually rewrite this as log with this base equals the exponent. And then I'm basically, whatever this is, I'm going to divide it by 4, the entire thing, and I'm going to end up getting 6.7 years. Okay, so you can type all of this into a calculator, and you should get about 6.7 years. And that makes sense. That's a reasonable answer. It didn't even double, so it doesn't take a whole long time. It doesn't take 50 years. That would be if you wanted something to double or triple or quadruple, depending on the interest rate. All right, so we're done with that one. So the last thing that I want to review is just our rational functions. We work with rational functions a lot in pre-cal. So we want to make sure that you remember how to do them. It does require a lot of factoring. You want to have your week 5 notes handy. Don't forget about Bobo, Botan, Eats, DC. I feel like I didn't remind you of that when we were doing our rational unit. Don't forget that Bobo means this is only true on when you're looking to graph, okay? By the way, this is not going to happen on this front page unless they ask you about asymptotes. So horizontal asymptotes are decided by Bobo, Botan, Eats, DC. if your rational is bigger on bottom, your horizontal asymptote is going to be 0. If your degree is bigger on top, you're going to have no horizontal asymptote. And if the exponents are the same, like the degree is the same on top and bottom, you're going to divide the coefficients of the top and the bottom, like the leading coefficients of the top and the bottom. I forget how they write that. Maybe it's like A over B, something like that. So I'll remind you of that when we get there, but I don't think I reminded you of Bobo Bot eats DC, and you'll use that all the way through calculus. I remember when my son came home from a calculus test, AP calculus test, and he was like, I failed my test because I forgot about Bobo Bot eats DC. It sounds stupid, but it does pay off to remember it. So I needed to remind you guys of that acronym. It just helps. Okay, so the first thing we're going to do is just simplify. That's all we're being asked to do up here is simplify, simplify, simplify. So that requires factoring, because what we're looking for is there anything that's a common factor on top and bottom that we can cancel out to simplify? So this is a difference of squares. That's x plus 1, x minus 1. And this is a pretty easily factorable denominator. And what I do see is I have a common factor on top and on bottom that I can cancel out. So my simplified rational is just whatever's left on top and whatever's left on bottom. Do you remember how to add, multiply, or divide rationals? So multiplying, first of all, you just need to factor everything, okay? And then you can look at everything that's on the numerators and everything that's on the denominators, and anything in any of them. If it's strictly a multiplication or division problem, you can cancel out anything on the top with anything on the bottom, even if it's not part of the same original factor, okay? If there's division, you need to flip this to become a multiplication problem. So as soon as you flip it, you can turn that into a multiplication as well. So I'm going to factor everything. I can take a 2 out of both of these, and that's going to leave me with a difference of squares, because I'll end up with x squared minus 25, and that breaks down like this. This is easily mental math factorable. X minus 10, can't do anything with that. If I take a 4 out of this and an x, because that's what they both have in common, I should go ahead and show what I did over here. So that became that. This will become the numerator, since it's a division problem, and x squared minus 100 is really x minus 10 and x plus 10. That's a difference of squares. And then this I will factor and put now on bottom. And so basically this turns into one giant numerator and one giant denominator, and anything that I can cancel out that's the same on top and bottom, I can and I should. Well, there's a lot that cancels out. So if you look at what's left, I can do 6 divided by 2, that leaves 3. So if you look at what's left, there's a 3 and a 4x on top. What's left on bottom is just x minus 5, and that is my answer. That is what is left. That is simplified. Okay, don't forget, if there's division, you have to flip it in order to be able to do all of this. And then can we add and subtract? Now this doesn't look like adding or subtracting two rationals together, but we really do have to, because if this has a fraction bottom with an x minus 10 on bottom, remember you have to have, for adding and subtracting, you have to have a common denominator. I'm just going to write that right there. And so if this has an x minus 10 on bottom, this needs to have an x minus 10 on bottom. And the only way I can do that is by turning it into a fraction that has an x minus 10 on both top and bottom. Remember, it's always a fraction. It's just a 1 on bottom, and we don't bother to show that. But I need to multiply both the numerator and the denominator by x minus 10 so that I have that common denominator on bottom. So the bottom is definitely going to be x minus 10. The top I need to combine. I have 3 plus 7 times x minus 10. That would be 3 plus 7x minus 70. And if I combine that, that would be 7x minus 67. And that is not simplifiable any further than that. So that would be my answer. All right, vertical asymptotes. Vertical asymptotes are any solutions of factors left in the denominator. So you have to try to simplify a rational before you can look at any vertical asymptotes. okay? So I can see that this could be factored as x plus 10, x minus 9, and this can be factored 2 times x minus 9. These cancel out. So what's left is a denominator where there are no x's. If there are no x's left in the denominator, then there are no vertical asymptotes. There's nothing left to solve for in the denominator, okay? There were no factors left in the denominator that you could solve for. So you're actually going to stick with that. If you had been left with some factor in the denominator that had an x, you would set that equal to 0, and that would be your vertical asymptote, or there could have even been more than one. All right, horizontal asymptotes. This is your Bobo bot and eats DC. And I've already written that up there. So you will know whether it has a horizontal asymptote of 0, or no horizontal asymptote, or horizontal asymptote that's equal to the division of these front coefficients by the degree. This is a quadratic. It's not been multiplied together, but it's a quadratic, a power of 2 on top. This is a power of 2 on bottom. So this is where the exponents are the same. If I multiplied these all together on top and all together on bottom, I'd have a power of 2 as the highest power in both. So you're going to divide those coefficients. So this 2 and this 1 I'm going to divide, and that's going to give me a horizontal asymptote. And you will choose one horizontal asymptote, and you're going to type in the equation, y equals 2. All right, we're almost done. 2 more problems. So can we graph a rational? That requires you to identify the vertical asymptote, if there is one, a horizontal asymptote, if there is one, an x-intercept, if there is one, a y-intercept, if there is one, and a hole, if there is one. So you won't actually necessarily always use all of these, but there are up to 5 features that you have to identify. The very first thing you want to do is factor to simplify. That should always be your first step. Okay, so if I look at the top, and it may not be factorable, but you should always try. I have a negative that I want to take out in front of this because this now is factorable. So if I take that negative out, I have a difference of squares. And my simplified rational looks like this. All right, so is there a vertical asymptote? Yes, there is something to solve for in the denominator. So your vertical asymptote, you're going to set x minus 4 equal to 0, and that's going to give you a vertical asymptote of 4. So when you plot it, when you click this, it's going to give you a vertical asymptote to go drag. Horizontal asymptote. Well, we have a degree of, this is a linear on top and a quadratic on bottom. So our horizontal asymptote is a Bobo, okay, bigger on bottom. The degree is bigger on bottom. So y equals 0 is going to be my horizontal asymptote. When you click the horizontal asymptote button, make sure you drag it to 0 if it's not already there. Does it have a hole? Did we cancel out a factor on top and bottom? If factor canceled in numerator and denominator, yes. So x plus 4, when I canceled that out, if I had instead solved for that x value, I would get negative 4. Then you need to plug in that x value, plug into reduced function. So what we ended up with is what you're going to go plug in a negative 4 into. So negative 3, negative 4 minus 4, negative 3 over negative 8. So my whole is at negative 4 and 3/8. So I'm going to click whole, and I'm going to drag it to negative 4 and just kind of just about halfway between 0 and 1. You're estimating, you have to. If you get a fraction or a decimal, plot it as close to the location as possible. X-intercepts. Solve for any x's left in the numerator. Do we have any x's left in this reduced fraction numerator? No, so this one has no x-intercepts, so you are going to leave that alone. And then y-intercepts, you're just plugging in a 0, plug in 0 for x into the reduced radical or rational. the reduced function. So plug a 0 in for x, and that gives me 0, 3/4. So I'll just go plot that right here. And as soon as you have found everything that you can, you'll hit plot rational function, and it will give you what your rational function is going to look like. So you don't click this until you've identified all features. Okay. Otherwise, it's going to prematurely plot your graph for you, and you may not have added all the pieces that you needed. Okay, and then the last thing, what if we don't have a graph? What if we just have an equation? We should be able to use that, right? And you have these buttons to choose if one of these or more is not present. So if we look at this, we can see that it's the same degree on top and bottom. They're both linear. So this is a EATS DC. Exponents are the same. Divide the coefficients. So 3 divided by 2, we will use that. Is there anything to factor out of these? Can I factor anything out of 3x plus 14? Can I factor anything out of 2x plus 3? I can't. So this is my original and my reduced function. So is there a denominator with an x in it? Yes. So you're going to set that equal to 0, and that's going to give you your vertical asymptote. Okay, your x-intercept is anything in the numerator with an x in it. You will solve for that. And so that will give you negative 14/3. And that's what we will write right here. Your y-intercept, you're going to plug in a 0 everywhere you see an x. And that ends up giving you 14/3. So that's what I'm going to write right here. And then is there a whole? Is there anything to cancel out on? Did anything cancel out on top and bottom when I factored or attempted to factor the top and the bottom? No. So you're going to choose there's no whole. You only have a whole when you do like what we did up here where we had a factor cancel out on top and bottom. And that is not the case here. And we are done. So congratulations, you survived. Have a great rest of your summer.